This is lecture 6, part 3, and I'm going to modify the cathode ray tube to look at things bigger than the electron, describe how ionization occurs and how the resultant ions can be analyzed, and then I'm going to describe the principles of mass spectrometry. So again, just to review, we have the basic cathode ray tube, which creates a beam of electrons that can hit a target. In other words, they're ballistic. If one puts into the path of the electrons a vapor, a gas, or atomic vapor, they become targets of the electrons, and they can become ionized as the ballistic electron collides with the neutral atom and knocks an electron off the neutral atom or molecule. In the earliest version of this experiment, the tube, which I've just completely erased and I've just put in the relevant electrodes, the tube contains a gas at low pressure. So it could be hydrogen, it could be helium, it could be an atomic vapor. So if you had a little filament heating up sodium metal, you could get sodium atoms into the tube as a vapor. The critical component here is the annular cathode, which allows materials to pass through it. And so what you do is you create the electron beam, strikes the neutral species, creates an ion, positively charged, which gets directed in the opposite direction of the electrons. So now, if you put the analyzing electrode plates, in other words, the E field and the magnetic field plates parallel to the trajectory, you could measure the charge to mass ratio of the ions. And experiments of this type with different types of elements discern that hydrogen could be created in a positively charged particle, and the mass to charge ratio indicated that it was about 1,800 times that of an electron. If you put helium into the tube, you got two particles, or two types of particles, with an M to Q ratio of about 7,200 times that of the electron and 3,600 times that of the electron. So you were getting species of helium plus and helium plus 2. If you put lithium vapor in, and that's done the same way as the sodium, you got three positively charged particles with M to Q ratios of about 12,600 times that of the electron, 6,300 times that of the electron, and 4,200 times that of the electron, namely lithium plus 2, lithium plus 3. So as a result of these types of experiments, you're beginning to get a picture of how the atoms are assembled. Namely, there's a number of electrons that are associated with heavy particles that are positive, and the light particles, which are negative, can be knocked off relatively easy. And there's a relationship between the number of positive and negative particles that constitutes an atom. And the atom itself has a balance. There's an equal number of these positive and negative things, one of which is really heavy, so the idea of the nucleus, and the other being very light, so like little satellites flowing around the nucleus. So this is how it becomes evident, or a more better experiment, shall we would say, that what distinguishes the elements is the number of positively charged particles at their core, the atomic nucleus, in other words. But I draw your attention to the fact that these same types of atomic number systems, atomic weight systems, were identified in the gasometry experiments when you compared the different gases, and we went through this in quantitative analysis. So this is reinforcement of work that was done in the early 1800s, in fact. So again, everything's reinforcing. We're learning that the elements are distinctive based on their weights. And we're refining that slightly by saying that the weights are actually related to the number of charged particles at the nuclear core of the atom. In illustrating the principles of mass spectrometry, I like to use an example of cats with dangerous hobbies. So the cat, our principal cat, is Boris. Boris likes to play with cannons, and the projectiles fired out of Boris's cannon come in various different sizes and weights. So on a given Sunday afternoon, one can find Boris at the park with his cannon, firing off his projectiles into the expanses of the park. Sometimes he amuses himself and puts cheese out in the park, attracting mice, and likewise firing at the mice. The entertainment part of this aside, the point of all of this is that if you fire a lighter projectile, a heavier projectile, it's not going to go as far. So the principal point of mass spectrometry is to recognize that light projectiles travel far, heavier particles travel less far. If we look carefully at what's going on, we recognize that the principal elements of this experiment are objects to be weighed, a device to propel the objects at a certain velocity, and a field of force, in this case gravity, that's perpendicular to the direction of the velocity, pulling them off, deflecting them in effect. So you're deflecting an otherwise linear trajectory and using the deflection to essentially indirectly measure the weight of the object. And that's what we saw in the case of the cathode ray tube, right? We had an electron gun which propels the electrons in a linear fashion, and then we know that you can focus that beam. And then secondly, we had a set of electric plates, or plates that would apply an electric field perpendicular to the direction of the trajectory and thereby deflect it according to the mass to charge ratio. So let's look now at the construction of a mass spectrometer. We start with a high vacuum chamber where we can get neutral species, they can be atomic or they can be molecular, produced at a low pressure, so fairly low density. I can put a box alongside of that initial chamber and I can put a higher vacuum, so a lower pressure in the right-hand box, and create a pinhole in the common wall. As a result, you'll get what's called an atomic or molecular beam as the species on the left-hand chamber start to pass to the lower pressure side on the right. If I now modify that chamber on the right by introducing an electron gun, I create a crossfire. So I'm bombarding the neutral species as they pass through the pinhole, and I create ions. Once I have created the ions, I can analyze their mass to charge ratio the way I did in the cathode ray tube, and mimicking what Boris does with his cannon and the projectiles. So if I introduce an analyzing box, again with a second pinhole in common with the chamber in the middle, I can have a set of electrodes that focus the ionic beam, and then what I need to do is create the same field for deflecting. So I introduce an electric field combination, and I introduce a magnetic field perpendicular. So electric field in one orthogonal direction, the magnetic field in the second. And then all I need now is what's called a Faraday cup or a detector, where the ions are allowed to crash into and create an electric current when they do so. So by knowing the dimensions of my box and playing around with the electric and the magnetic field, I can focus the ionic beam onto the detector, the fancy name for which is a Faraday cup, and I can measure the current, knowing that the beam is now striking it. So from the relationship of the electric field, magnetic field, the velocity, the curvature of the trajectory, I can determine the mass to charge ratio of any of the ions coming through. And this is the essence of mass spectrometry.